Hey Mavs, have you ever wondered how the world is gonna end? Pandemic? World war? No, you haven't? Well, I wanted to end with robots. Why robots, you may ask? Well, one, they're freaking awesome, and two, why not? So I'm gonna build a robot finger that could totally end the world. So you might be asking me, Corbin, why? And Corbin, how are you gonna make it? I don't know, that's what I'm gonna figure out now. I thought it sounded cool. So first we need to get the 3D models and print them. That won't work. So I have all the 3D printed parts here, but I need some components. Let's find something cheaper. Let's see what I have laying around here. Oh, look, a motor. What a coincidence. So I have everything I need right here, and now it's time to assemble. So we need to attach all the finger parts to the board. The way I'm doing that is using 3.0 filament and just putting it through. Now I'm gonna do it for the rest of them. So here's the vision. This will be attached onto here with fishing line going through the finger on both sides. Hint why there's two. When the servo motor spins, one line, the bottom one, will get longer and the one on the inside will get shorter, causing it to contract. Once it turns back, this one will get shorter and this one will get longer, letting it come out again. So after about an hour of work and 2 meals, it's time to attach everything together. Now that we have everything put together and we can put on our final piece, snap that on, and let's get to the programming. This slide imports the servo, this one defines the servo, this one attaches it to the pin 2, this loops through all the functions, alt to middle turns the servo 90 degrees, alt to rest puts it back to the regular, alt to max puts it 180 degrees. Now in the loop, we put alt to middle, delay, back to the middle, delay, turn it again, delay, rip. So if I've done everything correctly, when I upload this, the finger should turn and work. As you can see, it sort of works. Now you're probably wondering, is that it? Is this the finger you promised us? Well, no, it isn't. This is Bob. He's an AI walker using the same idea from the robot finger. Bob wants to learn how to walk from point A to point B, but doesn't know how to. He will start out at point A and train over and over until he learns how to walk. The AI's goal is to get from point A to point B as quickly as possible and use as little energy as possible. How will we train it? PPO. PPO stands for Proximal Policy Optimization. It has the perfect balance between performance and comprehension. Unlike others, it is a more simple algorithm that can be easily explained. Just like humans, Bob has 2 legs. Each leg has 2 joints. We have to teach Bob to walk by applying the torque on these joints. Therefore, the size of our action base is 4, which is the torque applied on 4 joints. For this, we will make the range -1, 1. This is what we call action space. In order to teach Bob how to walk, we need to give him rewards. Just like training a dog. When they do something good, you give them a treat. If they do something bad, you say no. I made it so Bob will receive a positive reward based on how far he's traveled. If he falls, he will get a punishment of -100 reward points. There's a little negative reward proportional to the torque applied on the joint to make sure he uses little energy as possible. Now, the action space defines the distribution used for action selection. The distribution is used to sample or select the action based on the specific distribution. And for a given action, the distribution defines its probability, which is plugged into this formula. This is the PPO probability formula. Now, what does this do? The distribution defines the action selection and its probability. In other words, movement. Now let's talk about the critic model. The primary role of the critic in continuous action space doesn't change from discrete. The model is learning to evaluate if the action taken by Bob led our environment to be in a better state or not, and give its feedback back to Bob, telling him if it was good or not. Here's what that looks like. Oop, too fast? One more time. Oh, didn't see it again? Well, too bad, it doesn't really matter. Anyway, I don't really know why I do this. Anyways, after a few hours of coding and 20,000 steps of training, we can see that it only took about 6,000 steps to get around 300 reward points. Notice on this graph, it starts out below 0, then when it receives a higher reward point, it learns to keep it. That's how the PPO algorithm works. Good job, Bob. Now, how in the world does this relate to the finger we made? Well, here's a vision. Imagine you have 2 of these attached to a main body. This could start of an AI walking legs. Now, of course, it isn't perfect, which means we have to train it for years and years before it's perfect. So don't worry, no robot will take over anytime soon.